Good afternoon, everyone. Welcome to this session of CHENG 415. In this session, we'll continue solving problems of chapter 11 or chapter 12, if you have the soft copy, 11 hard copy, 12 soft copy. We solved two problems, and today we'll solve the third problem. This is problem 12.3. It says here, a process has the transfer function g of s is equal to 2 exponential minus 0.2 s over s plus 1. Compare the proportional integral controller settings for the following design approaches. So he wants me to design 4 controllers. The first controller is a direct synthesis controller with tau c equal to 0.2. The second controller is again direct synthesis controller, PI direct synthesis controller with tau c equal to 1. And then the ITAE, integrated time weighted error, absolute error, and integrated time weighted absolute error, one for disturbance and one for support. Now, once I do this, he is asking me in part E to give a summary about the controllers. Which of these controllers that we will be designing, the 4 controllers, which one of them will be the most conservative, and which of them is the most aggressive or less conservative. And then finally, the final question for the 2 controllers of part E, simulate the closed loop transfer response to unit step disturbances, assuming that GD is equal to G. In fact, I'm going to simulate all the controllers to show you how to do the simulation. But the first thing we need to do is to derive the system first, derive the controller for A and B, and talk a little bit about direct synthesis to show you how to do the derivation. So let's move into the whiteboard and try and do the derivation. So for the first thing we want to do is we would like to write the process model, which is equal to 2 exponential minus 0.2 s over s plus 1. This is given to us. And since it says G, so I will assume, and he didn't talk in the question about any measuring device, any valve transfer function. So I will assume that this model here encapsulates everything, combines everything. Now for the direct synthesis, there are many things to consider. First of all, I want PI. Why I want PI? Because he told me in the question, he told me that I need to design a PI direct synthesis, a PI controller. So irrespective of what I do in direct synthesis, the outcome of the direct synthesis method should always be a PI. That is what's the recommendation of the question. Now, how do I change the structure of the controller in the direct synthesis? I have 2 options. Option number 1, I can play around with the structure of the direct synthesis controller by changing the shape of the y over y set point. Because this y over y set point desired is something that you choose. Based on what? Based on the desired response. So basically what you are saying, if you have a second order and you choose y over y set point to be a first order, you say, okay, I know that the process is second order, I know that the process is second order, but I want the controller setting to try and produce, once I close the loop, once I start setting or putting the controller on, I want the loop to respond as a first order. So depending on the selected y over y set point desire, you are forcing the process to go into your desired set point. Of course, we would always like to have y over y set point desired equal to 1. Why? Because this will give us the best performance. Immediately, the set point is equal to the, or the output is equal to the set point. But this is unreasonable and unrealistic. You cannot make this equal to 1. You have to have, the system has to take its toll. The process has to go through its dynamics. And also, there is another recommendation in your book saying that if you have a time delay in the system, it is always recommended that to use time delay in the y over y set point desired. Why? Because this time delay is a natural occurring phenomena of the process. You cannot ignore it. By ignoring it, you oversimplify the problem. So based on these recommendations, I can now say that I want my y over y set point desire to be a first order plus time delay response. Why? Because this is a first order plus time delay, so I just want it to be a first order plus time delay. Now, based on either the recommendation of the question or based on your preference, you can always choose tau c. In the question, he told me that tau c is equal to 0.2, so I'm going to use tau c equal to 0.2. What about theta? Well, for the case of theta, I would rather use the same theta given in the model. Why? So they can cancel each other. So just to summarize, just to recap, the first way I can control the direct synthesis controller output or controller setting is by the suggested y over y set point desire. Now I have been forced to use this because there is time delay in the original model, and it's a first order model, so there is no lowest than a first order, so I have to take it as first order. He have already given me that, he said that in part A, I want you to take tau c equal to 0.2. So tau c is already given to me. And I will assume theta equal to 0.2. Why? So that they both cancel once I start putting the direct synthesis for me. So let us proceed now. Let us write the direct synthesis equation. The direct synthesis equation GC is equal to 1 over G times y over y set point desire over 1 minus y over y set point desire. Substituting into this equation, the reciprocal of the model is S plus 1 over 2 exponential minus 0.2S. That is the reciprocal of the model. That is the model. And that is the reciprocal of the model. This is multiplied by y over y set point desired exponential minus 0.2s over tau c, which is 0.2s plus 1, divided by 1 minus exponential minus 0.2s over 0.2s plus 1. Now, as you can see, by writing the equation this form and by taking the model y over y set point desired is something you choose. So by choosing theta to be equal to 0.2, I can now cancel this with this. So I got rid of one of the transfer functions. One of the time delay expression, leaving me with one time delay expression. So now I just need to simplify this equation further. So what I will do, I will multiply this bracket by this one, and try and simplify the equation. So this is equal to GC is equal to S plus 1 over 2 multiplied by 1 over 0.2 S plus 1 over 0.2 S plus 1 minus exponential minus theta S, or 0.2, sorry, minus 0.2 S. The whole thing is 0.2 S plus 1. Why? Because I multiplied by the denominator, so I kind of unified the denominator. Now I can strike this with this. And the final equation, GC, is equal to S plus 1 over 2, 1 over 0.2 S, then plus 1, plus 1 minus exponential minus 0.2 S. Now I have another problem, this time delay term. This time delay term prevents me from finding the equivalent PI controller for the system. I have to substitute for this term with an approximated polynomial. I have to do an approximation. I have two approximations. I have one or first order Paddy approximation, and I have Taylor series approximation. Now, which one should I choose? Well, this is another, we said that the first thing that you can control the structure of the controller is by y over y sub point desired. The second thing is by the approximation of the time delay. So by choosing a certain structure, by choosing, for example, 1-to-1 Paddy approximation, I will get a certain time delay structure, or sorry, a certain controller structure. By choosing another form, I will get another controller structure. Now you can take it from me and you can try it yourself, but if I choose exponential minus 0.2 S to be equal to one first order Paddy approximation, which is minus 0.1 S, 1 minus theta over 2S over 1 plus 0.1 S. If I choose this and I'll substitute here, I will get a PID. Try it. You can try it. So this is not sociable for me. Why? Because this will give me a PID, and I don't want a PID. Why? Because the question asked me for a PI controller. So substituting for a Paddy approximation will not give me a PID. Then what will give me a PID? Sorry, what will give me? It will not give me a PI. What will give me a PI? Well, if I assume that exponential minus 0.2 S, if I use Taylor series. If I use Taylor series, this will be minus 0.2 S. Zero order and first order Taylor series approximation. And you can refer to your textbook for the course CHENG 3 to 4 to understand how this comes or how we derive. But a Taylor series expansion will give me this form. Now, if I substitute into the original equation, I will get a PI. Now, I know that you might raise a question. Okay, now how do I know when to use this or when to use that? Well, most probably, unless you are asked to derive the equation, the question will ask you to do so. But as you work more examples, you will become familiar. But let me take it as a rule. 1-to-1 Paddy approximation will always give you, 1-to-1 Paddy approximation will always give you a PID. Most probably it will give you a PID. Taylor series will give you a P or a PI. Okay, let us now substitute in the original equation and see what we will get. So substituting this in the original equation, we have GC is equal to S plus 1 over 2 multiplied by, and now I will say that this is 1 over 0.2 S minus plus 1 and then minus 1 plus 0.2 s. So this with this is cancelled. 0.2 plus 0.2 is 0.4, and multiply by 2 is 0.8. So I'll have s plus 1 over 0.8. S plus 1 over 0.8. Now this is the form, but I'm still not getting a PID controller. You have now to separate these two terms. So I can say that GC is equal to, sorry, there is an S here, S and S, so 0.8S. So I can say now that S over 0.8S plus 1 over 0.8S. So what I did is just separated the S and the 1 since the denominator is common. Now S is cancelled with S, and if we take 1 over 0.8 as a common factor, I will have 1 plus 1 over S. 1 over 0.8 is just basically 1.25, and you could check that. Is 1.25, so GC is equal to 1.25 times 1 plus 1 over S. If you examine closely, this is tau I, and this is Kc. So take Kc equal to 1.25 and take tau I equal to 1. This is part A of the question. Now for part B, the only thing that has changed in part B is the value of tau C. Instead of taking tau C to be 0.2, you take it as 1. So we will follow the same procedure. Here, except that when you come to this point, it is not 0.2 because you have used tau C equal to 0.1. You have used tau C equal to 1, so it is S plus 1. It is S plus 1, and in this case, you can, so let us just rewrite. This is part A, part B. We have GC is equal to S plus 1 over 2 multiplied by S plus 1 minus 1 plus 0.2S. Okay, so this will cancel with this, and this will give me GC is equal to S plus 1, 2 times 0.2 plus 1 is 1.2, 1.2 times 2 is 2.4S, and then you separate 1 over 2.4, take common factor 1 plus 1 over tau 1. So in this case, Kc is equal to 1 over 2.4, which is equal to 0.42. So Kc is equal to 0.42, and tau I is equal to 1. So as you can see, tau I have not changed because tau C is only affecting Kc. Tau C is only affecting Kc. So this is B, this is A, and now before we go and do the simulation, in MATLAB, what we need to do is part C and part D. Part C and part D. Now, just before I move away from or going to part C and part D, I would like you to do some comparison between the two values. As you can see, Kc here is equal to 0.42 and tau I is equal to 1. Kc here is 1.25 and tau I is equal to 1. Since tau I in both cases are similar, we will exclude tau I from the comparison and we will focus only on Kc. The higher the value of Kc, the more aggressive the controllers becomes. As you increase the value of the proportional gain, the controller will be more aggressive. So in this case, this is more aggressive, and this is more conservative. Why? Because of the value of Kc. Now, does this make sense? Let us analyze. What you are saying here, you said to the direct synthesis method, I want to use a very small tau c. I want to use a very small closed loop time constant, 0.2. For that reason, the settings became more aggressive because you want the system to go back to steady state faster than the second case where you give it more time. You said, okay, no. Let us wait a little bit. I will give the time constant to be equal to 1, so it is more than 0.2. So then you are allowing the system to kind of have more time to reach to steady state. So we expect the smaller the value of tau c, the more aggressive the controller will be. Now let's go to part D, C, and D. In part C and D, he's asking us to do the integrated time-weighted absolute error performance index, basically using the table, one time for disturbances and one time for set point. So we need the table, this table here, to work out the controller settings. We need this table to work out the controller settings. So as per the specification of the question, he is asking for a PI. So one time for disturbances, one time for disturbances, one time for a PI disturbances. This is PI for disturbances, and the other time is for set point. We need these settings to calculate the controller settings. How do we do the controller settings? You follow this rule here. You follow this rule here. Unless you see B, you follow B. If it doesn't say B, you just follow A. How do we do that? Well, just easy. First of all, we take the P values. So the P values are equal to A is equal to 0.859 and B is equal to minus 0.977. Then you calculate Y, which is in this case KKC. So you say KC is equal to A 0.859 times theta. What is the value of theta? Theta is 0.2 without the negative over tau. Tau is equal to 1. From where I brought these values? From the model. This is theta and this is tau. This is theta and this is tau. So I put it as 0.2 divided by 1, and then this is to the power b. Divided by, because this is KKC, I have to divide by K, which is equal to 2. If you work out this value, you will find that KC is equal to 2.07. KC is equal to 2.07. Now for tau I will take the I values, the I variables. A is equal to 0.674. And B is equal to minus 0.68. Then Y, which is equal to tau over tau I. So tau over tau I. Tau over tau I is equal to what? Is equal to this value. A 0.674 times theta over tau to the power minus 0.68. Then you just cross multiply. So tau I is equal to tau, which is 1 over 0.674 times 0.2 0.68. And if you work this out, you will get 0.49. 0.49. This is tau I and Kc. This is Kc is equal to 2.07 and tau I is equal to 0.49. We know that as tau I decreases, the system becomes more aggressive. As Kc increases, the system becomes more aggressive. So this controller, because it has a very high Kc and a very low tau I, lower than the other controllers, this is the most aggressive controller. And this is true because it tries to eliminate disturbances, reject disturbances. So when rejecting disturbances, you have to be aggressive as much as you can. Now we go for set point, and we will do the same for set point. Okay, we go for set point. We will take these values. So we want B and A for set point tracking. So for set point tracking, we'll say that B is equal to, this is part D, B is equal to 0.586, and A is, this is A, sorry, this is B, B is equal to minus 0.916. So we will do the same. Kc is equal to K 0.586 times 0.2 to the power minus 916. 916. Calculate this, and it's going to give you the result, which is in this case equal to 1.28. For tau I, now for tau I, you got to be careful. Why? Because as you can see, tau I has a superscript B, which means that you have to do it according to B. So in this case, what is I? A is equal to, for set point, 1.03 B, and I'm putting B just to remind you that it's different than the way we did it before, and this is minus 0.165 B. So now the equation is different. We can say that tau over tau I is equal, tau over tau I is equal to A, 1.03, plus B minus 0.165 times 0.2 over 1, theta over tau. And then you can cross multiply and find what is tau I. In this case, tau I is equal to 1. So Kc here is equal to 1.28, tau I is equal to 1. So this is more or less similar to case B. More or less similar to case B. Okay, so let's just put some values here. So okay, so Kc is equal to 2.07 and tau I is equal to 0.4. This is case C, and here Kc is equal to 1.28, and this is case D. Now all what we need to do is simulate case A, B, C, and D, and see the difference between the controllers. See what we will get as a result of these different controllers. So what we will be doing now is going to MATLAB and trying to do the simulation of those controllers and working out how these controllers will respond. So let us go to MATLAB. Here is MATLAB, and here is Simulink. And here is the library, and I need to simulate these systems, one time for disturbance rejection, one time for set point tracking, and see the difference. So we will start with a controller by controller. So let us do the first build the feedback control loop. We will do it first for set point tracking, and then we'll do it for disturbance rejection. So what I need now is I need a transfer function to draw the model. So I'll go to continuous, take transfer function and drop it into the workspace. So just wait for a minute for the system to build the transfer function, and then once the system builds the transfer function, you can work with it. It takes time for the first bit, but once everything is smooth, you can work faster. Okay, so the transfer function now has been imported. I need to zoom a little bit so that you can visualize this. Okay, now I need to reconfigure this transfer function to represent the transfer function I am having, this transfer function here in the question. So it is 2 over s plus 1. So double click here and change this number into 2. Again, process again. And then you don't need to change anything down since it is s plus 1. Now this has changed. I need to add the time delay. The time delay is added by importing a transport delay block, this block here. So you import a transport delay block and you configure the time delay and you put the value without the negative. So in our case, the time delay is minus 0.2. So I ignore the negative sign and I just put the value. So it is 0.2 without the negative. Why? Okay. So now this is my process. This is my process model. I want to duplicate this because one time I'll be working for disturbance, one time I'll be working for set point, and I will assume that for both systems the disturbance and the as given to me, the disturbance and the process is always equal to this. So and then I can use a summation from math operation to add those two. Again, to play around with these arrows, these inputs, you can change this bar. This bar is the cursor above shift to the right hand side. There is a cursor which is the backslash. You have to hold shift and backslash. So I'm going to erase this and I'm going to put it in the middle, in the in the end, and just let us see if this does. Yes, it does the trick. So I have now from top and from side. So now this is the disturbance and this is the set point. One time I will do a disturbance rejection, one time I will do a set point tracking. The next thing I want to do is to add a controller. So I go to continuous and bring PID controller, or you can just assemble the controller yourself, but it is easier for me to use this PID controller. Now the first thing I want to do is configure this to be a PI, and then I will change the setting according to configure this to be a PI. Okay. Now I need also to close the loop. How do I close the loop? I go to math operation. I bring the summation and I put it here, and then I connect this here. Just don't forget to change this into plus minus. Plus minus. Before we conclude, we need a step change. Remember that one time you will do a step change in set point, one time you will do a step change in responses. So I need a source, I need a constant, and I need a step change. Why? You will see why in a minute. So I'm going to connect the constant into the disturbances and make this constant equal to 0, as if I am assuming 0 disturbances at the beginning. 0 disturbances at the beginning. And then I'm going to connect this step change here, and I will be configuring the step to be equal to 1, just from 0, 1, just to test how the controller will react to a step change. And then the step time, you can choose any time you want to introduce. I will introduce it at 5, so that I will allow for 5 minutes. The system is at steady state. Then suddenly you introduce the step change, so you can see before and after the step change clearly. Apply. Okay. Now I will also change the time here to say 50. We need 5 tau, and tau c is 0.2. Basically, we need 5 of 0.2. So 20 is more than enough, but I'm just giving 50 just to give it enough time. Now, this is my A controller. I need my B controller, and I need my D controller. All of them are set point. All of them are set point. So this is my A controller. So what I will do is A, B, and D are all set point. And then A, B, and C will be a disturbance. So I want another controller. Now the good thing about the about Simulink is you can combine these systems into subsystems. Okay. To do this, all what you need to do is go to source, and instead of using a step, you can use an input. So you can say this is input 1, and I can change this into SB just to represent set point. And this is input 2, which is disturbance. And I can change this into D. And then I go to sinks, and I use the same balloon, but the output 1, and I can call this output. Yes. Now, if you select this and group Control G, now I have a subsystem. Now I can remove these balloons because I know I don't need them any longer. I just put them to indicate the output and the input. And now you have your subsystem. So this is my closed loop transfer function. If I double click on it, you can see that this is my transfer function, and I can go, I can move up from here. So I have, this is my A loop A for the question. I can now duplicate this loop B, and I can do another one, loop C. If you don't want to group, you can do that. You can just add it as it is. Sorry, loop C, loop D first, loop D. Okay. Now all of these loops are designed for set point tracking. So basically, we have set point equal to 1, while disturbances is equal to 0. Disturbances is equal to 0. Okay, set point is equal to 1, disturbance is equal to 0, and I need a scoop. And I can configure this scoop to have more than one input. So I'll be having 3 inputs. You can have 2 choices. You can plug them on top of each other, or you can have one and then go to commonly used and use a mixer, a multiplexer. So it will mix all the outputs. Just double click on this, make this 3. So then apply, okay. And then this is connected here, this is connected here, This is connected here. Basically, you will have three colors, yellow, blue, and magenta, purple, or pink. The yellow represent A, the blue represent B, and the other one, the cyan or the magenta, sorry, the magenta will represent D. Now I need to configure the controllers so that I use the controller settings that I've generated as I was calculating. So we have controller A, we have KC. Now, remember one thing. This is KC, and this is KC over tau I. Just remember that when you are feeding the values. So this is 1 point, sorry, the first KC is, 1.25. The first one is 1.25, and this is 1.25 over 1. I am putting it like this just to tell you that this is Kc over tau I. Then I will go up, go for loop B, bring the settings of loop B. The settings of loop B is 0.42, 0.42, and this is 0.42 over 1. And then finally, and they are all set point changes. We'll go up and we go for loop D, and for loop D we have the settings 1.28 and 1. 1.28 and 1.28 over 1. Lie. Okay, now we can go up and we can simulate. Once the simulation finish, we can examine. Now, what do we expect? We expect that both A and B will be more or less similar because we've got similar settings, 1.25 and 1, 1.28 and 1. While B will be less aggressive. Why? Because Kc is less than the 2. Let us now see whether we will get this or not, what we expected, or it's different from what we expected. So now the simulation has finished. We can click and we can see. Now there are slightly some oscillation. This is due to the integration. We can adjust that one. Yep. So it may require some time. We may need to adjust the settings, but as we expected, the blue one, which is controller B, the blue one, which is controller B, these spikes are due to, they will disappear after some time. If we increase the time, you can see that they will disappear after some time. But as we expected, the blue one is less aggressive. So basically what you are saying, if you choose tau C very small, you will have an oscillatory response. If you choose tau C very small, you will have an oscillatory response. Also, the IA, the integrated time-weighted absolute error, is punishing the longer the system stays at in error. So for that reason, it gives you more aggressive controller. Let us try and extend the time and see if it settles down or not. As you can see, it is oscillatory, and this oscillation is due of it being a aggressive controller. So we can change the time and see if it settles down or not after maybe 150. And let us see if it settles. Still, it is oscillating. It is oscillating, and this is creating problem for you. Now, the best choice here is to use direct synthesis method with tau D, with tau C equal to 1. Increase the tau C to get more stable response. This system is unstabilizing if you use very small tau C, or if you use an aggressive method like the ITEE. So not always the ITAE better than direct synthesis. It depends on the situation. It depends whether you want very aggressive controller or less aggressive controller. Now let us see the other way around when it comes to disturbance rejection. So now we will switch. Instead of having change in set point, we'll be having change in disturbances. So we will make set point equal to 0, disturbances equal to 1. Set point is equal to 0, set point is equal to 0, and set point is equal to 0, disturbance is equal to 1, disturbance is equal to 1, and disturbance is equal to 1. And since A and B are direct synthesis, they have no distinction between disturbance and set point. The settings for direct synthesis will be the same. But for the other one, this one, we will now use the C settings, which is the disturbance rejection settings. And now let us change the settings. This is according to the disturbance 2.07, and this is 2.07 divided by 0.49. 0.49. Apply. Okay, and then go up. So all what we did is now set point is equal to 0, disturbance is equal to a step change. And let us see now. So the the yellow line is controller A, the blue line is controller B, and the orange line is controller C. And as you can see, the ITAE created instability in the system due to it being highly aggressive. So you can see that for a first order system, most probably using direct synthesis or IMC is much better than using ITAE. ITAE is more sociable for a higher order system, not a first order system. It will drive first order system to instability, as you can see. You can see now that the controller is oscillating, continuously oscillating. Now let me just check if I have done something wrong or not. Yeah, so as you can see, this is what we get when we compare the disturbances. So we've done comparison for both set point tracking as well as disturbance rejection, and we found that for set point tracking, first order system, ITAE is not your is not a very good choice. It's not a very good choice, as it kind of becomes much more aggressive, especially for first order system with a small time delay. Now, if we change the time delay into a larger and compare, you can find that ITAE becomes much better than the other methods, because as the time delay increases, the ITAE becomes much more efficient in controlling the system. So the aim of this question was to give you an insight about the methods. It's a comparison between direct synthesis, DS, and ITAE. So, and you have to be careful. Now, how do you gain this information? You gain this information by working extensively with these methods, and by working extensively with these methods, you can then know exactly which method is much sociable for which application. If you have no questions, I have 1 more minute. If you have no questions, I will conclude this session and wait for you in the next session. Okay, thank you very much for joining me. I'll be seeing you hopefully in the next session.